Welcome to Day 1 Notes. Today's unit starts us off on the topic of stoichiometry. If you hear some weird noises in the background, I've got an Amazon parrot who likes to talk when I'm talking. I'm actually recording this on our snow day. So I know this unit's going to be coming up, so I thought I'd give this a try. Hopefully you like this method of taking notes. Remember, you can always go back and review the notes at any time. They'll be linked right again in Classroom. So, after today, you should be able to calculate the number of moles of substance that can be produced from their coefficients when you have a balanced chemical reaction. And we're also going to take a quick review of the basics of how to balance a chemical equation. So the word stoichiometry is a little bit weird sounding, but it comes from a couple different Greek words. One is stoichion, which means element, and metron, which means measure. Stoichiometry, as a vocabulary word, which you should make a flashcard of, is the study of quantities as it relates to chemical reactions. Specifically, we're going to be looking at comparing the number of moles on the reactant side to the number of moles on the product side, and we're going to be using those in some interesting ways. So, be sure that you make a flashcard of stoichiometry. Stoichiometry should be on the front side and the definition on the back side. So, when we're balancing a chemical equation, we go through a lot of work. The reason why this is a lot of work, and is worth doing the work, is because it's going to give us a lot of information. So here's a balanced chemical equation. In reality, this chemical equation is basically saying you have one molecule of nitrogen, remembering that nitrogen is a diatomic molecule, so you're always going to have two of them together. We have one molecule of nitrogen. In our chemical reaction, we also have 3 molecules of hydrogen, another diatomic element. So there's our first molecule, second molecule, and third molecule. This will produce 2 molecules of NH3, which is ammonia. And there's the second one. So this equation is basically showing this relationship. For every 1 molecule of nitrogen, you're going to need 3 molecules of hydrogen, and that's going to produce 2 molecules of ammonia, or NH3. When you're balancing your equation, you can actually, if you were asked how many atoms of nitrogen are on the reactant side, well, we have 2. How many atoms of nitrogen are on the product side? Again, we have 2. This is another way to look at this balanced chemical equation. Remember, the law of conservation of mass states that you can never lose atoms. You cannot lose mass. So the weight that's on this side is always going to total the weight that's on this side. Matter is never created or destroyed. We can also look at a balanced chemical equation by talking about the weights of the different substances. So if we get the mass of 1 mole of nitrogen gas, again, each one of these atoms is going to weigh 14.01. We have 2 of them. So the mass of 1 mole of nitrogen gas is going to be 28.02 grams. The weight of the hydrogen, we have 3 moles of hydrogen gas. Each mole would weigh 2.02 grams. We have 3 of them, so we multiply that together. And this would be the weight of our hydrogen atoms together, or 3 moles of our hydrogen atoms. Now we have to calculate the weight of 2 moles of ammonium, which would be 34.08 grams. The reactant side will always equal the product side. This is the law of conservation of mass, or conservation of matter. Here's our chemical equation again. Now we can look at the relationship of the number of moles, which are these coefficients. Well, we've got 1 mole of nitrogen gas plus 3 moles of hydrogen gas will produce 2 moles of NH3 or ammonium. These coefficients are now going to become very important in our being able to use this chemical reaction in a useful way. You have to be sure that the coefficients in your balanced chemical equation are the smallest whole number of ratio. Be sure that you cannot divide any of your coefficients by 2 or 3 or another number. Make sure that you've got them reduced down to the smallest number. So examples of mole ratios for this particular reaction we've been looking at would be the number of moles of nitrogen compared to the number of moles of hydrogen compared to the number of moles of NH3. We could also look at the number of moles of hydrogen it takes to produce 2 moles of NH3. So here's the relationships you get. The ratio of how many moles of nitrogen to the product, how many moles of hydrogen to the other reactant, and how many moles of the product to the hydrogen. So let's take a look at this in not such a chemistry format. Let's look at it with sandwiches. So here's our chemical reaction right up here. 2 pieces of bread, there's our chemical compound, plus 1 piece of cheese, another chemical compound, will produce 1 cheese sandwich. Down here, this is another fat interactive. So you can see we've got our reactants and our products and anything we have that's left over. Because in stoichiometry, we're really looking at how much of a product is going to be produced and what will we have as leftovers. So let me just go ahead and click around in this a little bit. You can see that I'm building cheese sandwiches over here. When I've got 2 pieces of bread, 1 piece of cheese, it gives me 1 sandwich. If I have an extra piece of bread, I've got my 1 sandwich, and now I've got an extra piece of bread. I can go ahead and manipulate these, and you'll be doing this interactive in just a few minutes, but stoichiometry allows us to be able to accurately create the amount of product we want and to know exactly how much of a reactants we're going to need to do this. We're going to look at a lab that deals with airbags and having the right amount of product produced so that your airbag fills to the correct amount. All right, so now what I'd like you to do is to pause this video and go back to Classroom. Click on the link that you'll see in Classroom that's right in the Notes section, and you'll be taken to an interactive that's going to let you explore this concept just a little bit. So pause this video, don't close out of it, just pause it, and then come back in a few minutes when you've done the moles ratio in chemical equations link. All right, so now we're ready to try a couple actual problems. Hopefully you've completed that activity on moles ratios and chemical equations. That'll help you understand what we're doing in this next section. So here's our first problem. If 3.86 moles of potassium react completely with more water than you need, how many moles of hydrogen would be produced? Well, let's start with our word equation. Potassium plus water will produce potassium hydroxide and hydrogen. Now notice how this has been crossed off to write hydrogen hydroxide, because we can look at water as being HOH as far as its chemical formula. Hydroxide is an OH. So let's take a look at this in symbols and it'll make a little more sense. There's our potassium. There's our water, H2O, or HOH. Potassium hydroxide. There's our hydroxide. Remember, you can always find any of these odd polyatomic ions on the back of your periodic table so you know what the formulas are. And then hydrogen, and hopefully you know now that this hydrogen must be written as H2 because it's a diatomic element. So when I balance my chemical equation, these are the coefficients I have. 2 moles of potassium to 2 moles of water to 2 moles of potassium hydroxide and 1 mole of hydrogen. Now, I do this with a regular dimensional analysis. I know I have 3.86 moles of potassium. I'm trying to find out how many moles of hydrogen I need. These are the relationships that we need. We need to know how many moles of potassium will produce 1 mole of hydrogen. So there's our what we start with, thrown over 1 so it looks pretty. Now, we have to make sure our units cancel out. So moles of potassium and mole of potassium, these will cross off. So now all I need to do is get the coefficient from potassium and enter it right there. On this side, moles of hydrogen, well, we have 1 mole of hydrogen. Cross off my units, and I'm left with what I needed in my unknown. And that will be the answer, 1.93 moles of hydrogen. Let's try another one. How many moles of aluminum will react with 0.512 moles of hydrochloric acid? Let's go ahead and write this in words. Pause the video for 1 second and see if you can write down what this equation will be. We've got moles of aluminum will react with moles of hydrochloric acid. There's our hydrochloric acid. This is going to be a single replacement. So I have aluminum chloride and hydrogen. Notice how we've written hydrochloric acid to be hydrogen chloride. There's our hydrogen chloride right there, hydrochloric acid. Aluminum chloride, and hydrogen, remembering that hydrogen is a diatomic element. There's the balanced chemical equation. I know I've got 0.512 moles of hydrochloric acid. I'm asked to find the moles of aluminum. These are the relationships I'm going to need. How many moles of aluminum per moles of hydrochloric acid? Dimensional analysis. Setting this up so my units will cross off. 6 moles of hydrochloric acid is going to be needed for every 2 moles of aluminum. Cross off my units. Now I'm ready to get the answer. 0.171 moles of aluminum will be produced in this reaction. All right, so if you have any questions, you're going to be able to ask me these over at the practice station, and that's where you need to move now. Basically, just come to me and get worksheet 1, and we'll work through a couple of these problems together, and then I'll turn you loose to do the rest on your own.